In section 4.6, we are going to be taking a look at another technique for solving non-homogeneous linear higher order differential equations with constant coefficients. So again, the problem looks like this equation right here, a y double prime plus b y prime plus c equals some non-zero function f of t. And we're going to try to find the particular solution. So again, we start by finding what is called the homogeneous solution. In fact, I'm going to put a little h right there to indicate this is y sub h. Remember that we solved this by solving the polynomial equation am squared plus bm plus c equals 0. We find the roots m1 and m2, and we can use that to create a y1 and a y2, a fundamental set of solutions. And so the homogeneous solution looks like this. Now, in the last section, 4.4, when we used method of undetermined coefficients, we made a guess, a hypothesis. We chose a specific form that we expected the particular solution y sub p to be in, and thus we tried to solve it based on those undetermined coefficients in that form. We're going to try a different strategy. We're going to take a different angle on this, and here's what we're going to do. We're going to look at this solution right here, this y sub h that I have written right here, and I'm going to highlight it. Notice its form. It looks like a constant times y1 plus a constant times y2. What if we were to hypothesize that we could write a particular solution also based on y1 and y2, but instead of having a constant out front, we have these now functions v1 and v2. All right, so we're going to try to find, are there such functions v1 and v2 that would make this format, this thing that I have now in blue here, an actual solution to the original differential equation. So we're going to try to find something. Now remember, y1 and y2 often look something like e to the m1x and, m1t, and y2 might be something like e to the m2t. Of course, it might also involve sines and cosines if your roots are complex. But in the end, we're going to have some kind of function like that here. And now we're again trying to find what are these v1 and v2 that would make this new function a solution to the original non-homogeneous differential equation. All right, so if we assume that, then what I'm going to do is I'm going to plug in yp prime and yp double prime and, of course, y sub p all into equation 1 here and see what happens. Now I'm going to clear up a little bit of what I have here on the screen. Let me erase a little bit of this so we can see this a little better. Let's assume yp looks like this, right? What is y sub p prime then? Y sub p prime would be we're going to use the product rule here and here. So first times the derivative of the second on the v1 y1 would be v1 y1 prime plus v1 prime y1 plus, now same thing with the second one, v2 y2 prime plus v2 prime y2. And I'm just going to rearrange for a second because what I want to do is actually make our lives a little bit simpler with an additional requirement. So let's put these two terms here together, and let's put these two terms here together. And the result is I'll write it as v1 y1 prime plus v2 y2 prime plus a v1 prime y1 plus v2 prime y2. And just so that this resulting form is easier to solve, and I'm going to kind of do this out of the blue here, so just take my word on it for now, and you'll see later on why this makes sense. v1 prime y1 plus v2 prime y2, let's assume that that is 0, so that really all we have now for yp prime is v1 y1 prime plus v2 y2 prime. So if I didn't have this in there, I've got these extra terms in here. So what I'm going to do is I'm going to add a constraint on my v1 and my v2 so that this statement right here has to be true. Okay, so I've already labeled this as equation 2, and that's important. So I'm going to come back and do that. Now, using what I've just written down, assuming that this whole thing right here now is 0 by that assumption, we're going to have yp prime I can now take its derivative to get yp double prime again, so I can plug it back in into this equation here. No, not that equation, sorry. Up to this equation up here, equation 1. All right, so yp double prime, if I take the derivative, I have to use, again, the product rule. So first times the derivative of the second. Derivative of y prime is y double prime, plus the second times the derivative of the first, so that would be a v1 prime, y1 prime, plus v2 y2 double prime, plus v2 prime y2 prime. So now I'm going to substitute, in fact, I'll do this in green. I'm going to plug this here and this, and of course the original yp, all back into equation 1. So if I do that, here's what I get. In fact, I'll do it right down here. Remember, we have ay double prime plus by prime plus cy. So if I plug yp into each of these, and again recognizing what we know them to be from what's highlighted in green, I have a times yp double prime, which is v1 y1 double prime plus v1 prime y1 prime, plus v2 y2 double prime plus v2 prime y2 prime, plus a b times yp prime is v1 y1 prime plus v2 y2 prime, plus now c times v1 y1 plus v2 y2. I'm just leaving off the part where it says of t. All right, now let's rearrange this a little bit. This is all equal to, let's put all of these terms that I've got in arrows together. That's all the v1, y1. Since they all have a v1 in common, I can factor that out. And this looks like v1, y1 double prime with an a out in front, plus y1 prime, undo, from here, from this arrow right there, I've got a by1 prime, and from this arrow down here, I pull out the v1 and I've got a cy1. And the reason why I did all that is because this now has to be 0. That has to be 0 because y1 is a solution to the homogeneous equation. Way back up here, I made this statement right here that y1 and y2 are linearly independent solutions to the homogeneous. That means if I plug in y1 with an a and a b and a c coefficient in front of it, that is a y1 double prime plus b y1 prime plus c y1 would have to be 0. Now, that took care of this term, and this term. So let's do that again now with these terms. Boom, boom, and boom. Pull out a v2 out of each one of those, and I've got an a y2 double prime plus b y2 prime plus c y2. And again, because y2 is a solution to the homogeneous equation, that's all going to be 0, which takes out these terms here. And what I'm left with is plus an a times v1 prime y1 prime from here, and a v2 prime y2 prime from here, and this has to equal, right, because we're plugging into equation 1, has to equal f of t. Actually, you know what? I think on the next page I'm using g of t, so what I really meant to have here is a g of t. That's what the book uses. So this equals g of t. Just notation is all the difference there. And so if I divide the a across, notice I have exactly what is written right here, right? V1 y prime y1 prime plus V2 prime y2 prime equals g of t all divided by a. Now, if you take equation 3 and equation 2, you can write that as this system of equations right there. Now, remember, we know what y1 and y2 are. Those are the known values. So our unknowns, boom, 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 are in G. So we can solve for these unknowns as a linear system. This would just be like we could do substitution, we could do linear addition. I'm going to use my favorite rule for solving 2 by 2 systems, which is called Cramer's rule. Now, you may or may not have seen Cramer's rule before, so I'm going to go ahead and walk through how Cramer's rule is going to look, just so you can see where these things come from. But there is, in fact, I'll tell you what, I'm going to insert into this video a short explanation of how you can use Cramer's rule to solve that. All right, so let's talk about Cramer's rule. All right, Cramer's rule is a shortcut way to solve something that looks like ax plus by equals c, and say dx plus ey equals f. Okay, so you can use determinants to write down the solution. So say we're trying to find the x's and the y's, right? Turns out x and y can be written in terms of the 2 determinants, 2 by 2 determinants on top and bottom. Okay, and same thing for y. It is a determinant over a determinant. Okay, I've always referred to this as just the giant H is what Cramer's rule is. What you do is in the denominator of both of these, you put the determinant of the coefficient matrix, A, B, D, E. A, B, D, E. That's the numbers that are out in front of the x's and the y's. Now on top, what you're going to do is you're going to take the right-hand side and stick it into whichever column of the variable you're looking for. So put a CF, which is the numbers on the right-hand side, and then leave the other column alone, BE. So it looked just like A, B, D, E, but I replaced the first column with the right-hand side. And this one down here, start with A, B, D, E, and just replace the second column with the right-hand side. Then what you can do is use your rule for calculating 2 by 2 determinants, right? Forward diagonal minus back diagonal in each case, and you'll be able to have a formula immediately to write down the solution. So this would be CE minus BF over AE minus BD. That will give you the solution to the linear system. AF minus CD on top of AE minus BD. All right, just to show you a quick example here, let me scroll down a little bit, and let's take maybe 2x plus 3y equals 5, and 3x minus 2y equals 1. All right, so you could solve this using substitution or other techniques, linear addition, where you'd multiply by something that makes the variables cancel out when you add up the two equations. But you can also do this in your head almost immediately with Cramer's rule. On bottom, you'd have 2, 3, 3, negative 2. On top, you'd put a 5 and a 1 and still have 3, negative 2. So again, it's the coefficient matrix, but I replaced the first column, since I'm solving for x, with the 5 and the 1, the right-hand side. So that's negative 10 minus 3 over negative 4 minus 9. That's negative 13 over negative 13, which equals a positive 1. Y would do the same way. Determinant over determinant. 2, 3, 3, negative 2 is the coefficient matrix in the denominator. Of course, we know that's going to be negative 13 on bottom because we've already done that calculation. On top, I'm going to have the same first column as the bottom, but now I'll replace the second column with a 5 and a 1. So that now becomes 2 minus 15, or negative 13 over negative 13, turns out to be 1. So the solution is 1 comma 1, which you can double check if you plug back in here. If you plug a 1 and a 1, you get 2 plus 3 is 5, check. And you plug in 1 here, you get 3 minus 2, which is also 1. So there's your solution using Cramer's rule. Now I'm going to apply Cramer's rule back to the system we were looking at with variation of parameters. So here's our system that we want to solve for. We're solving for v1 prime and v2 prime because those are our unknowns. So v1 prime would be a determinant over a determinant. Okay, so the first, the denominator we know would be y1, y2, y1 prime, y2 prime, which by the way looks familiar. That happens to be the Wronskian of y1 and y2. On top, you now replace the first column with these right-hand side values, namely whatever is 0 and g over a would happen to be. G being the right-hand side, a being the coefficient of the y double prime in your original equation. And in the second column, still the same, is y2 and y2 prime. Okay, so you end up with a negative g over a y2, and on bottom you get y1 y2 prime minus y1 prime y2. Of course, you can move that a down to the bottom and have negative g y2 over an a times y1 y2 prime minus y1 prime y2, which by the way happens to match exactly what you have down here in your notes. You do the same thing for v2 prime. The denominator will be the same as the coefficient matrix in the determinant. The numerator, we're going to keep the y1 column the same, and now the second column becomes 0 and g over a, so we get g over a times y1 all over y1 y2 prime minus y1 prime y2. Again, you can move the a to the bottom, so gy1 over a y1 y2 prime minus y1 prime y2, just the same thing we have right down here. Okay, and so these formulas right here give you enough information to come up with an expression for v1 and v2 because they're the derivatives. So to find the actual values of v1 and v2, we use these integrals right here. So now we've shown we can in fact find a v1, v2 so that this expression right here is a solution to the non-homogeneous equation. A little bit complicated. Really all it boils down to is knowing this formula right here and plugging it into that equation right there. We've derived it. So in the future, what I'm going to do when I use variation of parameters, the name of this technique is I'm going to first find y1 and y2 using my homogeneous equation. Then I'm going to use v1 and v2 formulas here to find those v's so that I can put them in here and have a yp. And that would be it. All right, so let's look at an example and walk through that so you can do this also in your homework. In this example, our goal is to find a solution to y double prime plus y is equal to the tangent of t. And the reason why I put a constraint on the domain, or I guess the values of t, is because the right-hand side of my differential equation would have points of discontinuity. So let's just look from negative pi over 2 to positive pi over 2. So here's the process you would go through to use variation of parameters. Step 1 is to find the homogeneous solution. That is, we want to know what's the solution to y double prime plus y equals 0. And you'll recall you use the characteristic polynomial m squared plus, remember it's always what derivative it is. So it was m squared because it's second derivative. This is the 0th derivative, so it's just going to be plus 1 equals 0. So you move this 1 to the other side, you have m squared is equal to negative 1, so m is plus or minus I. Okay, where this would mean your alpha is 0 and your beta is 1, because remember, when you have a complex number like this, you're thinking of it in terms of alpha plus or minus beta I. The real part is 0. The imaginary part is 1. So y1 is e to the 0t times cosine of beta t. And y2 is e to the 0t, which is 1, times sine of beta t. Now beta is now 1, so this is cosine of t and sine of t. So your y sub h is c1 cosine of t plus c2 sine of t. Now what we want to do is we want to find a particular solution that looks like some function of t times cosine of t plus some other function of t times sine of t. That's what variation of parameters assumes, and we're going to try to find v1 and v2. So what we know is v1 is the integral of negative g, which is tangent of t, times y2, which is sine of t, divided by y1. Now again, if you want to know where I'm referring to, I'm using these formulas right here in this box. So now I need my a, which is 1, times y1, y2 prime. y1 is cosine of t. y2 prime is the derivative of sine of t, which is also cosine of t. So that's cosine squared minus y2, which is sine of t, times the derivative of y1, which is negative sine of t, so that becomes a positive sine squared of t in the denominator, dt. Now the beauty of this is the denominator is 1. And on top, what do I have? I have negative tangent of t, sine of t. So this looks like integral negative tangent of t times sine of t. I'm going to rewrite this as sine of t over cosine of t times sine of t. So this is now the integral of sine squared of t over cosine of t dt. And actually, the easiest way to integrate this is to realize I can split this guy up here on top into something in terms of cosines. This is the integral of 1 minus cosine squared of t over cosine of t dt. And then I can write this in two fractions, this fraction and this fraction, which would give me the integral of 1 over cosine t. Oh, I lost my minus somewhere in here. There's a minus sign in here. Minus. So I've actually got a minus 1 over cosine of t plus cosine of t. If I distribute that minus that's out in front. Did you see where I lost that? I should be careful. Let's try this one more time. It's a minus sign here, so there's a minus sign out in front here. You distribute that to these two terms. You get a minus 1 over cosine t, and a minus and minus makes plus cosine squared over cosine, which is just cosine of t dt. That's negative secant. Oh, let's try that again. It's the integral of negative secant of t plus cosine of t dt. And the integral of secant, we can look up. That is not all that hard. It is negative natural log of secant of t plus tangent of t. And the derivative of cosine is sine of t. And I won't put my plus c because we just need one particular solution, not a general solution for the y sub p. So there's my v1. Now what about v2? v2 is going to be similarly the integral of g, which is tangent of t, cosine of t, and the denominator is the same. It's cosine squared of t plus sine squared of t. Again, using the formula for variation of parameters, right here that we derive for what V2 would have to be that solution. So the denominator, as before, is 1. So that gives us tangent of t, cosine of t dt. And this is even easier because this becomes sine of t over cosine of t times cosine of t. The cosine of t is canceled, so this is the integral of just sine of t dt, which we know the integral of sine is negative cosine. All right, so let's write this all the way out. Y now is V1 Y1, this is y sub p, plus V2 Y2. So V1, we just got, is negative natural log of secant of t plus tangent of t times, plus sine of t times y1, which was cosine of t, plus V2, which is negative cosine of t, times y2, which was sine of t. And what you should notice is if you distribute this cosine to each one of these, this second one cancels out with this one. And what you're left with is y sub p is equal to the negative natural log of secant of t plus tangent of t, all times cosine of t. So that altogether says that y is the sum of these two answers, c1 cosine of t plus c2 sine of t minus a natural log of secant of t plus tangent of t times cosine of t. There is your general solution. And notice, by the way, we could not have solved this example using the method of undetermined coefficients. So that's how variation of parameters allows us to find the particular solution in cases where, say, the method of undetermined coefficients would fail. And that's all you need to know to be able to begin tackling the homework. Follow the same example. Find your your y1, y2 first, like we did up here. On number 1, find your y1 and y2, and then find your v1 and v2, and then rewrite your your y sub p, as v1 y1 plus v2 y2. Once you have that, you can write down your final solution, which is y sub h plus y sub p. This equation here is your general solution to the non-homogeneous differential equation.